All right, we're going to continue doing homework problems out of chapter 19 and maybe get to some in chapter 20. I will post all of them later today. All right. Let's see. So I want to start at 1958. All right, a particular voltaic cell operates on the reaction zinc solid plus Cl2 gas yields zinc plus 2 and 2Cl minus. All right, so it says giving a cell potential of 0.853 volts, calculate the maximum electrical work. All right, so you have to remember that your delta G is equal to work max, and that is equal to negative NFE cell. All right, but we're not using a mole, we're using 15 grams. So 15.0 grams of zinc. All right, and your N is moles of electrons. So you have to see that your zinc is going to zinc plus 2. So your half reaction is zinc solid is going to zinc plus 2. To balance that, you need the 2 electrons. And so you need that for your mole ratio, 2 moles of zinc, 1 mole of zinc, 2 moles of electrons. All right, so we have to convert our grams of zinc into moles of electrons to plug it into our equation here. So you have your mass of zinc, you look at the periodic table, you get your molar mass of zinc, 65.41 grams per mole of zinc. So the grams of zinc cancel the grams of zinc. We don't want moles of zinc. We want moles of electrons. That's why we had to write the half reaction. We have 2 moles of electrons that are produced for every 1 mole of zinc reacted. And so now we have the correct units, moles of electrons. That is what your N value is. All right, so that's 0.459. All right, and so F is a constant, E is given. So once you have that solved, then this question is very simple. Delta G is equal to work max is equal to negative 0.459 moles of electrons. All right, and then Faraday's constant, 9.65 times 10 to the fourth. That would be given on the test, and that is coulombs per mole of electron. So the moles of electrons, not just moles of electrons cancel moles of electrons. And then they give us the 0.853 volts. And you can add another thing here, or you can just know that a coulomb volt is a joule. But here I know that a joule is a coulomb times a volt. So that's what happens to the unit of coulomb. That's what happens to the unit of volt. It is a joule. And so your delta G is equal to work max, which is the question. What is the maximum work? And that is a negative 3.78 times 10 to the fourth joules. All right, so your delta G, your work max, has to be in joules. So the key there is to know that you have to change your mass of zinc into moles of electrons. All right, 1960 is very similar. I will put that one up later, but you do the exact same thing. You have moles of electrons, and you find your delta G, which is your work max. So let's go to 1962. All right, order the following oxidizing agents All right, so we're looking at oxidizing agents. So when you're looking at an oxidizing agent, you're of course looking at the reduction half reaction. The reactant of a reduction half reaction is your oxidizing agent. All right, and so you want the most spontaneous reduction half reaction, which means you want the largest E naught value, the largest positive E naught value, because remember your delta G is equal to negative NFE. All right, so N is always a positive number, it's moles, F is a constant and a positive number. And so if your E value is positive, then your delta G is negative and it's going to be spontaneous. The larger your E value, the more negative your delta G, the more spontaneous. All right, so we're looking at, so this question is basically saying, I'm going to give you a list. Give me the one that has the most positive half reaction, your reduction half reaction with the most positive E naught value. That would be the most spontaneous. All right, so then they give you the list. All right, so they have Ag plus. You look on the table, you have Ag plus, plus 1 electron goes to Ag. You don't memorize this, it will be given. All right, the E value off table 19.1, 0.80 volts. So that is spontaneous. Is it the most spontaneous? Well, we're going to find out. The next one is cadmium. Off of your table 19.1, that has an E value of negative 0.4 volts. That one is non-spontaneous, so that is definitely not the, so right now Ag plus is the winner. All right, but then you got your MnO4 minus. You look on the chart, the reduction reaction for that in acidic solution is a positive 1.49 volts. All right, and so that's your answer. This is your largest positive E value. This is your strongest oxidizing agent. Because it is the most positive E value for the reduction half reaction. And this is your weakest oxidizing agent because it has the least positive, it's actually negative, value for your E. So the smallest value, negative 0.4, that's the weakest oxidizing agent, cadmium plus 2. The most positive is the MnO4 minus, so that is your strongest oxidizing agent. So these questions can be very difficult or quite simple. If you know what you're looking for, it's quite simple. All right, 1966. So a lot of these are, will the reaction occur or not? And that means, is it spontaneous or not? If it's spontaneous, the reaction goes in the forward direction. If it is not spontaneous, then the reaction does not go in the forward direction. All right, answer the following questions referring to table 19.1. Will oxygen oxidize iron 2? All right, so you have to look at your oxygen. And we want to oxidize our iron 2. So Fe plus 2 can only be oxidized to iron plus 3 plus 1 electron. So the way you're going to see it on the chart is your Fe plus 3 plus 1 electron goes to Fe plus 2. You've got to reverse it. We want to know if it can oxidize this. So on the chart, you have your E value. You have to take the opposite sign for that E value. All right, and so when you look up that E value, it is, oh, I can't read my writing here. So the oxygen one, I can read that one. Plus 4H plus goes to 2H2O. And that one releases, no, that one is plus 4 electrons. Of course, you don't need to memorize these. These are on table 19.1. Your E value here is 1.23 volts. Your E value here is negative 0.77 volts. So when you add these up, even though you have to, when you add these up, multiply this by 4 in order for 4 electrons gained to equal 4 electrons lost, you do not multiply your E value. So it's still negative 0.77. And so when you add those together, you get a positive number, so minus 0.77. All right, so you get a 0.46 volts. All right, and so that E value is positive, that is spontaneous, this reaction occurs. That is spontaneous in the forward direction. So spontaneous means you're forming products. So yes, the oxygen will oxidize your iron plus 2 to iron plus 3. So if you get a positive E value when you add those two up, the answer is yes, that will occur. If it is negative, it would be non-spontaneous, and no, that would not occur unless you added some voltage to that system. Will copper metal reduce nickel plus 2 to metallic nickel? All right, so we have to look up our nickel plus 2 being reduced to nickel solid. Again, you're going to find that number on the periodic, on the table 19.1. All right, so that is a reduction potential. So that one we just go right off of the chart. All right, and when you look at the chart for your nickel, that is a minus 0.23. All right, and so will copper metal reduce it? So if you look at copper metal, it goes to copper plus 2 electrons, the E value for that. You have, that is the opposite of what it says on the chart because that is an oxidation. So we have a negative 0.34 volts. And of course, when you add up two negative numbers, you get a negative number. And the answer here is no, it will not. So your final is a negative 0.57 volts. And so non-spontaneous, which means it does not give you products. So this is a no reaction. This will not occur unless you add a 0.57 voltage to that. So the answer is no, the copper will not reduce nickel plus 2 to nickel. If you looked at the opposite reaction, and so if it just changed and said, will nickel reduce copper plus 2 to metallic copper, you got to reverse both of those reactions. You get a positive 0.57 volts. Yes, that would occur. So again, if you reverse the reaction, the cell reaction, you reverse the sign of your voltage. All right, so you're just looking at your voltage. If your voltage is positive, it is spontaneous, and yes, that reaction will occur. If it is negative, it is non-spontaneous, and no, that reaction would not occur. All right, 1970. Calculate the standard cell potential for this notation. You have Sn solid, Sn plus 2, salt bridge, I2, phase change, I minus. That is a bad cell notation. All right, it has to start with a metal. It must end with a metal. If it doesn't end, if the end does not have a metal, then you use the inert electrode platinum. All right, so they do not have a proper cell notation here. All right, but they didn't ask for the cell reaction. They simply said, give the cell potential. All right, but I'm going to give the cell reaction as well. So you have your anode. Always start with your anode. You got your salt bridge. And you got your cathode. So always, that's the way it is going to be. Anode is oxidation, so Sn goes to Sn plus 2 electrons. Of course, on the reduction potential 19.1, that is going to be the reverse of that, so you have to change the sign. So when you change the sign, that is a positive 0.14 volts. All right, so then you look at your iodine. So you've got your I2 plus 2 electrons right off of the chart, going to 2I minus. You read it right off the chart. Your E value is 0.34 volts. And so then you simply add this up. You don't have to multiply anything. You got 2 electrons gained, 2 electrons lost. You simply add the E values and you get a 0.48 volts. And so your cell voltage is 0.48 volts. This should be a very easy question. Sn plus I2 goes to Sn plus 2 and 2I minus. There's your cell reaction, and there is your cell voltage. All right, you're going to be given all the voltages. You just simply, you have to know you're going to give the reduction potentials. When you do oxidation, you got to change the sign. First the reaction, you change the sign. You multiply it by something, do not change the value for E when you're multiplying through to get electrons gained equal electrons lost. All right. Let's do 1972. All right, what is the standard cell potential you would obtain from a cell 25 using the electrode in which a Hg2 plus 2 is in contact with mercury metal? So plus 2 electrons goes to 2Hg. An electrode in which an aluminum strip is dipped into an aluminum plus 3. So we have Al plus 3 electrons going to Al. All right, so this reaction is either you're gonna have to reverse one of these because they're both written as a reduction potential. And so in order to know which one of these needs to be reversed, you have to find your E values. When you look up your aluminum, it is negative 1.66 volts. And when you look up your mercury, it is 0.80 volts. All right, so if you reversed your mercury, you would have two negative numbers and you add that up and you get a larger negative number, and that would not be spontaneous. And so it should be very obvious that you have to reverse the E value that is negative in order to make that positive and give you a cell reaction that is spontaneous. All right, so you have your Hg2 plus 2 electrons goes to 2Hg. And then you have now reversed, you have your Al going to Al plus 3 electrons. So off the chart, right off the chart, 0.80 volts. We reversed our aluminum, so now that is the opposite sign. That is a positive 1.66 volts. We want the cell reaction, and so we have to multiply the Hg by 3 to get 6 electrons gained. We have to multiply the aluminum by 2 to get 6 electrons lost, and you have to know to not multiply your E values. So your E cell is 2.46 volts. All right, and then the cell reaction, if they ask for the cell reaction, that is a 3Hg2 plus 2 2Al goes to 2Al plus 3 and 6Hg. There is your cell reaction. All right, so that pretty much does everything that you need to know. When you reverse one of them, you change the sign. When you multiply them through, do not multiply your E values. These should be relatively easy questions to get right. All right, let's try 74. calculate the standard free energy state at 25 degrees for the following. Use standard electrode potentials. All right. So we're looking for, you have to understand the question, standard free energy change. You have to realize that that's saying find delta G. That is your free energy change. And so that is equal to negative NFE naught cell. All right, so we want our delta G, 25 degrees Celsius, standard. All right, and so then they give you a reaction. You have your 4Al plus 3O2 plus 12H plus going to 4Al plus 3 plus 6H2O. All right, so that is your cell reaction. All right, and so you have to break it up into the two half reactions. So you have table 19.1. You see that you have the same one we just had. Al is going to Al plus 3 plus 3 electrons, and that was 1.66 volts. We just had that up above. So that was the 1.66. Of course, on your chart, it says negative 1.66, but you see that the aluminum is not the reduction, it is the oxidation, so it is a positive 1.66 volts. You also see that you're going to multiply this by 4 because in the balanced reaction, there's 4 and there's 4. Also, you need to remember, you do not multiply your E value by 4. All right, so then on your chart, you see that you have O2 plus 4H plus, this is coming right off of your chart, plus 4 electrons, that's off of table 19.1, that goes to 2 H2O. And then the E value right off the chart, because that is a reduction half reaction, so that's going to have a reduction potential. That one is 1.23 volts. All right, and so we also see that we had to multiply that by 3. So the reason why you had to multiply it by 4 and 3 is because you had to have the same number of electrons gained and lost. So now you see that that number is 12. All right, and so you add that up, you get the reaction that they gave you. What you're looking for is the E cell. So that is simply add those up. That is a 2.89. That is a spontaneous reaction. Delta G will be negative. All right, so delta G is equal to negative NFE naught cell. That's the standard delta G. All right, so you just plug in your numbers. Delta G naught is equal to negative 12 moles of electrons. 12 moles of electrons gained, 12 moles of electrons lost. F is Faraday's constant, 9.65 times 10 to the 4th coulombs per mole of electron. And then you have just calculated your E cell at 2.89 volts. And again, a coulomb volt is a joule. You can write it, you can just put it, whatever. A joule is a coulomb times a volt. So the coulombs units cancel, the volt units cancel, and you have your units of joules for your delta G. All right, and so when you push the buttons on your calculator, you get your delta G is equal to negative 3.35 times 10 to the 5th joules. All right, so that would be the same answer if they asked for work max. Your delta G is also equal to work max. All right. 19.80. Calculate the standard cell potential of the cell corresponding to the oxidation of oxalic acid by the permanganate ion. So they give you a reaction. And that reaction is 5 H2C2O4 plus 2 MnO4 minus plus 6H plus yields 10 CO2 plus 2Mn plus 2 plus 8 H2O. All right, so now it says that you can find the MnO4 minus on table 19.1, but you cannot find the oxalic acid. It is not on table 19.1. And so the question then says you're going to find the delta G for this reaction. We're at 25 degrees Celsius, and so your delta G for this reaction is equal to your delta G products minus delta G reactants. All right, so you're going to find all of your numbers from Appendix C for your oxalic acid. It is negative 698 kilojoules per mole. That one actually had to be given to you. That was given to you in the problem. It is not listed in table Appendix C in the back of the book, so they had to give that to you. Your MnO4 minus, negative 447. H plus, 0. Your CO2 gas is negative 394.4. Mn plus 2, negative 228. And then finally, your 8 H2O liquid, negative 237.1. All right, so you got to take 10 times your number here. So multiply that by 10 moles. You got to take 2 times your number here because you have 2 moles. You have to have 8 times your number here because you have 8 moles of water. All right, so you add all those up. That is your delta G of your products. Then you write that number there. Then you do your reactants. You have 5 moles of your oxalic acid, so 5 times your negative 698 kilojoules per mole. You have 2 times your negative 447, and you have 6 times 0, which is 0. And so then you put that total right here for your delta G of your reactants. All right, and so then you take your product number, subtract your reactant number, and you get your delta G of your reaction. And if you do that, you will get negative 1.91 times 10 to the 6 joules. All right, so you would have your answer in kilojoules, then you convert it to joules, and so you have a negative 1.91 times 10 to the 6 joules. All right, but the question wasn't what is delta G? The question was what is your E cell value? All right, but we know that the delta G is equal to negative NF E cell. So the same equation we used last time, but this time we have the delta G and we're finding E. Last time we had E and we found delta G. All right, so we just plug in our numbers, but we do need to know what is our moles of electrons. So you do have your table for your MnO4 minus going to Mn plus 2. So in this reaction on your table 19.1, or if you don't want to look at it and you just want to do it yourself, but the answer is there. This is a minus 8, so Mn is a plus 7 oxidation. This, of course, is a plus 2 oxidation. All right, and so it is gaining 5 electrons per Mn, and you see that we have 2 Mns. And so now we know that we have 10 electrons gained, and they balanced it for us. And so there's also 10 electrons lost. So the hardest part of this problem, there's a lot of hard parts, there's a lot of numbers to get your delta G correct. And you have to find your n value. But if you look at table 19.1, you will see this, and it will have the 5 electrons, but you have to see that you multiplied it by 2, and so it is 10 electrons. All right, so you put in your negative 1.91 times 10 to the 6 joules, and that is equal to negative 10 moles of electrons, F 9.65 times 10 to the 4th coulombs per mole of electrons, and then you have your E naught cell. All right, so you just divide both sides by negative 10 and 9.65 times 10 to the 4th, and you get your E cell. All right, and so your E cell, delta G, was negative. That means it is spontaneous. That also means that your E value is going to be positive. It's going to be positive because you have a negative here with your delta G. You got a negative here in your equation. And so that gives you a positive E value. And when you push the buttons, you get a 1.98 volts. All right, so that question has a lot of math, a lot of ways to make a lot of different errors. So that would be a difficult question. All right, 1984. Use electrode potentials to calculate the equilibrium constant. All right, so now we have our equations. Delta G is equal to negative NFE. We also have that is equal to negative RT ln KEQ. All right, so we can get our electrode potential, so we don't have to do the delta G of this one. But if you're given a chart, you could find the delta G as well. But the question says use electrode potentials. All right, so it is very clear that you are to use the electrode potentials for this problem. ClO4 minus plus ClO2 minus yields 2 ClO3s. All right, and so you look, okay, so this one is not in your chapter. It is not in table 19.1. You have to go to appendix I for these electrode potentials. ClO2 minus plus 2 OH minus yields ClO3 minus plus H2O plus 2 electrons. Table appendix I. All right, and that E value is negative 0.35 volts. So the E for this is negative 0.35 volts. All right, and so that is losing electrons, and so you're doing an oxidation. So it was a positive 0.35. You saw it in the reverse direction because it is still a reduction potential appendix. All right, the ClO4 minus plus H2O plus 2 electrons in appendix I yields ClO3 minus plus 2 OH minus. And the E value for this one, that one's written right off of the chart, is a 0.17 volts. When you add those up, you get your E value of negative 0.18 volts. All right, so this one is a non-spontaneous reaction. All right, and so when it is non-spontaneous, you know that you're going to have a very few products, lots of reactants. You're going to have a very small number for your KEQ. And so you have your equations. Delta G is equal to negative NFE, which is equal to negative RT ln KEQ. And we're looking for the KEQ. All right, and so then we have, we can multiply through by negative 1 and have an NFE is equal to RT ln KEQ. Then we divide both sides by RT, and so we can have our ln of KEQ is equal to NFE over RT. And then we would push our E to the X button to get our KEQ. So now we just plug in our numbers. So N is 2. 2 moles of electrons, 9.65 times 10 to the 4th coulombs per mole of electrons. That's your F. Your E, we calculated, negative 0.18 volts. Divided by the R value, you have to use the 8.314 joules per mole Kelvin. And then the temperature is 298 Kelvin. All right, so that's all equal to your ln of KEQ. All right, so then you would push your E to the X button to get KEQ is equal to 8.1 times 10 to the minus 7. All right, so we knew that it would be a small KEQ. This is non-spontaneous. Therefore, very small KEQ. Very few products. It does not go to the right. Very few products, mostly reactants. You're going to have a very small KEQ. All right, now we're going to go to 1986. And we're going to use the Nernst equation. So the Nernst equation is your E cell is equal to your E naught cell minus RT over NF ln of Q. All right, so Q has the same expression as K, except Q is not at equilibrium. All right, so E cell, this is off of table 19.1. So you will calculate your E naught cell off of table 19.1. All right, E cell, you're either going to calculate it or it has to be given. When you're looking for Q, that of course is your concentration of products over reactants. But remember, if you have a gas, the gas has to be in atmospheres. So then it would be, if you give a gas, it's not concentration, it is pressure of your products. All right, and pressure of reactants. All right, if you're given a pressure, and that has to be in atmospheres, and this has to be always in molarity. So any gases in atmospheres, any concentrations in molarity. All right, so when it says what is the cell potential, you're looking for E cell. All right, and so now we're not, your E naught cell is 25 degrees Celsius. These are still going to be at 25, but at E naught cell, all concentrations are 1 molar, all pressures are 1 atmospheres. Your E cell is when you have different starting concentrations. All right, and so here is the reaction, the cell reaction. You got your nickel solid, nickel plus 2. And when you're doing your cell notation, you always have to put in the concentrations. So your nickel plus 2 is 1 molar. Your SN plus 2 is not 1 molar. It is 1.5 times 10 to the minus 4. All right, so you write your reaction. Always first is always the anode, and then the salt bridge, and then your cathode. So the anode is oxidation. Nickel goes to nickel plus 2 electrons. You look on table 19.1. You remember that this is an oxidation, and so you have to reverse your E value. And that is a negative 0.02, if I'm reading this. No. That is a, 0.23. 0.23 volts. All right, then you have your reduction is Sn plus 2 electrons goes to Sn. Your E value for that, right off the chart, do not have to change the sign. Do not change the sign. It is right off the chart. It's a reduction, 0.14 volts. And so when you add them up, you already have 2 electrons gained, 2 electrons lost. So you don't have to multiply by anything. So you simply have your nickel plus Sn plus 2 yielding nickel plus 2 and Sn with an E value of 0.09 volts. And so we know it's going to be spontaneous. So we know that the K value would be a large number. It is a spontaneous reaction. But we're not looking for K, we're looking for Q. And so the setup is the same. So Q and K is the same. So it's the products concentration of your nickel plus 2 over reactants concentration of your Sn plus 2. Remember, no liquids or solids will go in there. If it were a gas in this reaction, you would put pressure in atmospheres. All right, but they give you those numbers. They tell you that your concentration of nickel is 1 molar. And they tell you that your concentration of tin is 1.5 times 10 to the negative 4. And so now you just push the buttons to get your Q value, or not, just plug that in the way it is. All right, and so your E cell, that's what we're looking for, is equal to your E naught cell. What you get off of the chart is your E naught cell, 0.09 volts, minus your RT, 8.314, temperature 298, over N, 2 moles of electrons canceled on both sides, and then your F, 9.65 times 10 to the 4th. Now, note that your book will always take these three, never change. It's always 8.314, it's always 298, it's always 9.65 times 10 to the 4th. So they will have a number, and then they will divide it by N, so you still have to, so each reaction, you got to figure out how many moles of electrons are being gained and lost. But I always just write in all the numbers. And also your book many times uses log instead of ln. All right. But I always use the ln. And then I just have 1 over 1.5 times 10 to the minus 4. And then I push the buttons to get my E cell. And when I push the buttons, I get an E cell. Looks like negative 0.02. All right, so whatever you get when you push those buttons, I believe that's what I have written down. All right, so Nernst equation definitely will be questions on the test using the Nernst equation. All right, 1988. Calculate cell potential. Again, cell potential, that's your E cell. With the following reaction at 25 degrees Celsius. So they give you a reaction. Cr2O7 minus 2 plus 6I minus plus 14H plus yields 2Cr plus 3 plus 3I2 plus 7H2O. All right, so we're looking for the E cell of that, and they give us our concentrations. So the dichromate concentration, 0.02, your Cr plus 2 concentration, 0.015. Nope, that's the I minus. I minus is 0.015. The Cr is 0.4. H plus is 0.6. All right, so there's your concentrations. Of course, they don't give anything for a solid. They don't give anything for a liquid. That is not part of your expression. All right, and so then you have to look up your table 19.1. So you've got your Cr2O7 minus 2 plus your 14H plus, which yields your 2 Cr plus 3s plus 7H2O. No, not 7. Yeah, 7H2O. That is correct. Yes. All right, and so that one's right off of your chart. All right, except you will have electrons, because here you have minus 14, you've got a plus 12. So each Cr is plus 6 on this side. Each Cr is plus 3 on this side. All right, and so you have 3 electrons per chromium. You're doing that twice. And so this is on table 19.1, but that's why it has 6 electrons here for that reduction. So that one's right off the chart. You find your number. Your number is 1.33 volts. All right. All right, so then you do your other half reaction, which is your 6I minus goes to 3I2 plus, and we know it's going to be 6 electrons because it has to be balanced. All right, but the one that you see on the chart is 2I minus goes to I2 plus 2 electrons. You had to multiply it by 3 in order to get 6 electrons lost and 6 electrons gained. Even though you had to multiply it by 3, you do not multiply your E value right off the chart. Your E value is negative 0.54. All right, so then you add those up to get your E cell, E naught cell, to put in your Nernst equation. All right, and that is 0.79 volts. All right, so it is spontaneous. We know that you're going to have a very large K value. All right, so we know that this is a spontaneous reaction. Anytime you have a positive E, you have a negative delta G. All right, but we need to find the E cell value. We have the E naught cell value. We just calculated that. Minus 8.314. That never changes. 298. That's never going to change. N is what changes. You have to see by the reaction given that your N value is 6 moles of electrons. So what you need to get from this is your E cell, which we calculated, 0.79 volts. You had to get your moles of electrons from this, the 6, but everything else, well, not everything else, you also have to get your Q value. All right, and so then you have your 9.65 times 10 to the 4th. And now you have your ln of Q. So we do have to calculate Q. So we go back up to our equation that was given. And so we have our Q value. The expression is your products, which is your Cr plus 3 raised to its coefficient of 2. That's it for this side. That's the only ion. That's a solid. That's a liquid. We don't put solids and liquids in. Over your Cr2 O7 minus 2 raised to its coefficient of 1. I minus raised to its coefficient of 6, and H plus raised to its coefficient of 14. So you plug in the numbers that they give you. You plug in your 0.4, let's see, go this way. So to plug in your numbers, so you got your 0.4 squared divided by your chromate concentration, dichromate concentration, 0.02, and then your I minus concentration, 0.015, raised to the 6th power, and your H plus concentration of 0.60 raised to the 14th power in order to get your Q value. All right. And I got 9.0 times 10 to the 14th. So when you push that, 9.0 times 10 to the 14th is your Q value. So now we can plug that into our equation down here, 9.0 times 10 to the 14th. And then we can solve for E cell. All right, and when you push the buttons, you get 0.64 volts. All right, so yeah, that is the Nernst equation. Those questions are not easy. All right. Let's do, we'll skip the next Nernst equation. That's enough for those for now. Let's do a 1996. All right, now we're doing electrolysis. Now we're doing things that are not spontaneous. We have to add a voltage in order to get these to work. All right, and so your equations for electrolysis is Q is equal to IT and Q is equal to NF. All right, and so N is moles of electrons, F is Faraday's constant. Over here, you've got your current. This is in amps. And you got your time. This is in seconds. All right, your Q is coulombs. That's your charge. All right, and so these are the equations that will be used to answer electrolysis questions. And you'll know you have an electrolysis questions because it's going to have amps in the question. Anytime you have amps in the question, you are using these equations. All right, so you have your question. You have 2Cl minus going to Cl2 gas plus 2 electrons. All right, so you have the question, how long will it take? Okay, so time, how long will it take? All right, so now we know that we are solving for time, how long will it take to produce 2 kilograms of chlorine. So we have 2.00 kilograms of chlorine. If the current, okay, so that tells you for sure that you're using these these equations. When you have current is 500 amps, 5 times 10 to the second. 5.00 times 10 to the second amps. That's just simply 500 amps. All right, so F is a constant, and we want to find time. So if Q is equal to IT and Q is equal to NF, then I know that IT is equal to NF. All right, and we're solving for time, so just divide both sides by current. And so to get the answer, we simply take NF and we divide by I. All right, so the only thing we have 2 of these. We already know F, it's a constant. We know I, it was given, it's 500 amps. All we have to do to solve this problem is calculate N. All right, but just saying N is moles is not good enough. You must know that N is moles of electrons. And they give us the half reaction. So what we have to do is take our 2 kilograms of Cl2 and convert that to moles of electrons. So first we convert it to grams. All right, there's 1,000 grams in a kilogram. All right, so now we have grams. So that is 2,000 grams. We don't want grams, we want moles. So we need the molar mass of Cl2, 35.45 times 2, 70.9 grams per mole of Cl2. So now we have moles of Cl2. We don't want moles of Cl2, we want moles of electrons. That's why we have our reaction, our half reaction. That gives us our mole ratio of chlorine. 1 mole of chlorine is produced while every 2 moles of electrons are produced or released. All right, and so there's our mole ratio of Cl2 to electrons. And so now we have converted our 2 kilograms of chlorine to moles of electrons, the only other number that we needed. All right, and so that is 56.4 moles when you push the buttons. And so we're solving for time. So time was the NF, and we divided both sides by the current I. So now we just plug in our numbers. 56.4 moles of electrons. 9.65 times 10 to the 4th moles of electrons, or coulombs per mole of electrons, so moles of electrons cancel. Divided by 5.00 times 10 to the 2nd amps. All right, and so you have your moles of electrons cancel. All right, and a coulomb per amp is a second. And so your answer here is time in seconds. And that number has been converted to hours. It looks like 3.02 hours. All right, so that's in seconds. And so there are 3,600 seconds in an hour. And so I have converted the seconds into hours. All right, so you have to know these equations. You have to know the units. You have to know that this is time and the units must be in seconds or this does not work. Moles of electrons. There's only one unit that you're ever going to be given for current, and that's amps. And F is always a constant. But the T has to be in seconds. Whatever time is given, you convert it to seconds. And whatever mass is given, you have to convert that to moles of electrons. All right, let's do another electrolysis. That is 19.98. All right, how many grams of cadmium are deposited from a cadmium sulfate? So from this and table 19.1, you see that cadmium sulfate is cadmium plus 2. Because sulfate is a minus 2, it says an aqueous solution. That means it has dissolved. All right, and so what's happening is our cadmium plus 2 is being reduced to cadmium solid. So the question is how many grams of cadmium solid from an aqueous solution of cadmium plus 2. All right, and so you know that this is a Q is equal to NF and IT question because they say that 1.75 amps. So they give us I. Anytime you have amps in your question, you're using these equations. 1.75 amps flows through the solution for time as soon as you're given 325 minutes, you must immediately convert that to seconds, or these equations, the units, will not work. All right, and so you have 60 seconds in a minute. So you immediately convert that to seconds. And so it says how many grams of cadmium. All right, so now we have I, we have T, and F is a constant. So we can solve for N. N is equal to IT over F. And so you put in your amps, 1.75. You put in your time, must be in seconds, 325 times 60. You put in your constant, Faraday's constant, 9.65 times 10 to the fourth. And that gives you 0.35. And this, of course, is N, which is moles of electrons. The question wasn't how many moles of electrons. The question was how much cadmium. So now you have your balanced reaction, your half reaction, and you see that you have 1 mole of cadmium for every 2 moles of electrons. So you have 1 mole of cadmium for every 2 moles of electrons. And we have 0.35 moles of electrons. So now we have moles of cadmium. The question wasn't how many moles of cadmium were deposited, it was the mass. And so then you find the molar mass, which is 112.4 grams per mole off the periodic table. And so moles of cadmium cancel the moles of cadmium, and now you have your answer in mass, 19.9 grams. All right, and so we solved for moles of electrons, and then we converted that to moles of cadmium and then mass of cadmium. And so you're either going to be solving for N, or you could be solving for current. The first one that we did, solve for time. You're not going to be solving for a constant. That is, of course, a constant. All right. Let's do a couple of questions out of chapter 20. All right, let's get the easy ones. Make sure you get the easy ones right. 20.48. It says write the, well, they make that a little bit too easy. There's going to be at least one thing missing. So if I had a nitrogen 14.7 plus a 1,0 neutron, and that emits a proton. All right, so then the question would be, what is the other? The problem in 2048 gives you this answer. On the test, it's not going to be there. You have to be able to see that you have 14 and 1 on this side. And since you have a 1 here, you have to have 14 here. There's only going to be one thing missing. Again, the numbers on top have to equal on both sides. These should be very simple questions. You have 7 plus 0 is 7. That means your 6 plus 1 on this side is 7. You have 7, you have 7. Then you have to know that that is your atomic number. And so you just go to the periodic table and you see that atomic number 6 is a carbon. All right, and so this is a nuclear bombardment reaction. You have to know how to write the notation. The target nucleus is first. Then you have to know the symbols. The symbols for a neutron is N. The symbol for a proton is P. So that is the incoming particle. That is the exiting particle. And here's your product nucleus, 14.6. So you have to be able to balance a nuclear reaction. These should be very simple. All right. And if I go to 2050, it's the same type of question, just in reverse. So here's what the problem would look like on the test. You're going to have SC 4521. And then it's going to have N comma alpha, and then it's going to have a question mark. And it's going to say, write the nuclear reaction. So you have to know that you have your SC, which is your target nucleus. You have to know a neutron, and if you forget, it's probably on the test somewhere. So you can just look up at the previous question if you don't know the numbers of a neutron. All right, 1, 0, but you should know that it is a 1, 0. You have to know that it is a reactant. The first one is a reactant. That is the incoming particle. This is the exiting particle, the product. You have to know that an alpha particle is a helium-4 nucleus. And then you have to be able to figure out what is next. All right, so you have to have your numbers on top. 45 plus 1, 46. And then 2 plus 42 is also 46. So the top number has to be 42. You got 21 plus 0 is 21. 2 plus 19 is 21. And then you go to the periodic table and you find element number 19, and you find that that is potassium. All right, and so to answer this, there's your reaction, and this question mark is a K4219. That is the completed notation for that nuclear bombardment reaction. Let's do a radioactive decay. All right, let's do 2062. All right, so what you need to know is everything is first order in a radioactive decay. So you got neptunium, 237. All right, decay constant. So they give you the K value. Decay constant, you have to know that that means K, 1.03 times 10 to the minus 14. And it is first order, so it's 1 over time. And this time they give us seconds as our unit of time. And then it says calculate the half-life in years. All right, and so your half-life is equal to 0.693 over K. So that is very simple, 0.693. You put in your K value, 1.03 times 10 to the minus 14. 1 over seconds, except that is not your final answer because that is 6.7 times 10 to the 13. And that's in seconds. And the question was specific. Give your answer in years. All right, so you have your 60 seconds in a minute. You've got your 60 minutes in an hour. You've got your 24 hours in a day. You've got your 365 days in a year, and then you have your answer in years. Which is 2.13 times 10 to the 6. What else I wrote there? Okay, 2.1 times 10 to the 6 years. So the half-life is 2.1 million years. Some of these things are going to be around forever and ever. All right, so make sure you know how to do your half-lives. There will be half-life questions on the test for sure. Also, your mass. Make sure you know that you're going to take a reaction. So when you look at like 2080, you're going to take your mass, your change in mass, that's going to be your mass of your products minus your mass of reactants. All right, and we're doing a nuclear mass. So the table that's on 20.3, I think, has the mass of the elements. All right, so you will have to subtract the electrons. But again, if you're subtracting 20 electrons from the products and 20 electrons from the reactants, you don't actually have to do that. You can, but it's just going to cancel itself out. But if there is a different number of electrons on both sides, that will make a big difference. Remember, if you have a carbon-12 nucleus, so that is a nucleus, all right, so carbon-12, so that means you have 12 and 6. The mass number is the number of nucleons, so there are 12 nucleons per 1 carbon-12 nucleus. So if it's asking for nucleons, that means protons and neutrons in there. So just be aware of that. And also there's sometimes they ask for MeV rather than joules. It's just an energy conversion, and that conversion factor will be given. But make sure you are given the right units that the question is asking for. All right, but all these answers will be posted.